the beginning of time. We can actually see the beginning of time. Light that's been traveling for 13 billion years, since before Earth, our Sun, or even our galaxy existed, now reaches our telescopes, revealing the universe's earliest moments. In this documentary, we'll journey through the cosmos to witness 3 of the earliest galaxies ever discovered. Imagine peering into cosmic dawn itself, when darkness first gave way to light. These faint stellar ghost towns stopped forming stars during the universe's infancy, preserving ancient secrets about our origins. Their mysterious properties quietly challenge what astronomers thought possible, revolutionizing our understanding of how everything we know came to be. What existed before the stars began to shine? The answer takes us to a place beyond imagination, a universe shrouded in absolute darkness yet paradoxically filled with energy so intense it defies comprehension. Picture a churning ocean of particles packed so densely that light became trapped, a cosmic fog thicker and hotter than anything we know today. For approximately 380,000 years after the Big Bang, our universe existed in a state of blindness. This wasn't darkness as we understand it, the absence of light, but darkness because light existed but couldn't escape. Photons were constantly scattered like balls in a cosmic game of particle pinball, making the universe essentially opaque, similar to trying to see through a wall of superheated fog that would instantly vaporize anything familiar to us. As the universe expanded, it gradually cooled, reaching a critical temperature threshold. At this pivotal moment, electrons and protons, previously too energetic to bond, combined to form neutral hydrogen atoms. This process, called recombination, transformed the cosmos. Photons could finally travel unimpeded, and the universe, for the first time, became transparent. This transparency didn't bring immediate light. What followed was the cosmic dark ages, several hundred million years where the universe, though clear, remained in darkness. This vast expanse contained only diffuse hydrogen and helium stretching across immense distances. From this impenetrable cosmic haze, the seeds of light began to emerge. Gravity began its patient work on minor variations in density, causing hydrogen gas to pool in certain regions. These pools grew denser over millions of years, collapsing under their own weight to form the first hydrogen clouds. Eventually, these primordial clouds became dense enough at their cores to trigger nuclear fusion, birthing the first stars. Imagine watching this transformation, a hot, impenetrable cosmic stew clearing to reveal empty darkness, which then, after eons of gravitational gathering, begins to sparkle with the first points of light, like countless candles being lit one by one across the void. This shift from opacity to transparency, from uniformity to structure, created the framework for matter to organize itself, for gravity to shape the first stellar nurseries, and eventually, for the formation of the ancient galaxies we'll soon explore. From those primordial star-forming regions emerged brilliant galaxies and cosmic time capsules that mysteriously stopped evolving. While some early cosmic structures went on to form massive collections of stars, others seem to have frozen in time, offering astronomers an unprecedented glimpse into the universe's earliest days. Astronomers recently discovered 3 remarkable galaxies in the direction of NGC 300 that defy conventional understanding. These are ultra-faint dwarf galaxies, containing mere hundreds to perhaps 1,000 stars. For perspective, our Milky Way houses hundreds of billions of stars. Like silent relics from the early universe, these structures remained hidden until very recently. The discovery highlights how groundbreaking finds often come through persistence. During the pandemic, University of Arizona astronomer David Sand, frustrated by research limitations, turned to methodically examining DESI legacy survey images of previously overlooked regions. It took a few hours of casual searching, and then, boom, Sand recalled, describing the moment when the faint smudges suddenly revealed themselves on his screen. My heart rate actually jumped when I realized what I was seeing. The discovery highlights how groundbreaking finds often come through persistence. During the pandemic, University of Arizona astronomer David Sand, frustrated by research limitations, turned to methodically examining DESI legacy survey images of previously overlooked regions. It took a few hours of casual searching, and then, boom, Sand recalled, describing the moment when the faint smudges suddenly revealed themselves on his screen. My heart rate actually jumped when I realized what I was seeing. What makes these galaxies extraordinary is their pristine condition. Unlike dwarf galaxies near the Milky Way that are constantly shaped by gravitational forces, these three exist in isolation. This seclusion has preserved them in a nearly unchanged state for billions of years. When examined using the Gemini multi-object spectrograph, these cosmic fossils revealed only ancient stars, no young ones, and appeared completely empty of gas. In normal galaxy evolution, gas serves as the fundamental building material for new stars. Without it, star formation ceases entirely. This gas absence points to a cosmic mystery. What halted these galaxies' development so early? The leading theory involves reionization, a period when the first massive stars produced enough ultraviolet radiation to strip gas from smaller structures. We don't know how strong or uniform this reionization effect is, Sand noted. If we knew what fraction was affected, that would tell us something about the early universe that is very difficult to probe otherwise. These preserved structures are essentially cosmic amber, allowing astronomers to directly observe what galaxies looked like shortly after the first stars began to shine. Light from those primordial galaxies is literally carrying messages from the dawn of time. But there's something even more fascinating at work here. When you look up at the night sky, nothing you see exists precisely as you're viewing it. Even light from our own sun takes 8 minutes to reach Earth. By the time its photons touch your skin, you're experiencing sunlight that left the sun's surface while you were doing something else entirely, like receiving a snapshot from the recent past. Light from those primordial galaxies is literally carrying messages from the dawn of time. But there's something even more fascinating at work here. When you look up at the night sky, nothing you see exists precisely as you're viewing it. Even light from our own sun takes 8 minutes to reach Earth. By the time its photons touch your skin, you're experiencing sunlight that left the sun's surface while you were doing something else entirely, like receiving a snapshot from the recent past. Light travels at approximately 300,000 kilometers per second, an incredible speed that creates a fundamental paradox across cosmic distances. The farther away an object is, the deeper into its past we're seeing. Light from Andromeda, our nearest galactic neighbor, takes 2.5 million years to reach us. Astronomers observing it witness events that occurred when early humans were first appearing on Earth. The James Webb Space Telescope functions as a cosmic time machine by detecting infrared light that has been journeying through space for up to 13.5 billion years. As the universe expands, it stretches the wavelengths of light traveling through it. Light that began its journey in the visible spectrum billions of years ago gradually shifts toward the redder end, a phenomenon called redshift. The older and more distant the light source, the more dramatic this stretching becomes until visible light transforms entirely into infrared wavelengths. Equipped with a 6.5-meter mirror, JWS doesn't just capture light, it retrieves history. Its sophisticated near-infrared camera, capable of detecting wavelengths from 0.6 to 28 micrometers, unveils cosmic stories that would remain invisible to previous telescopes like Hubble. By measuring exactly how stretched this light has become, scientists can calculate precisely when it began its journey. The greater the redshift value, the older the light, allowing astronomers to place distant galaxies accurately on the cosmic timeline. Some of the light captured by Webb originated during the epoch of reionization, 400 million to 1 billion years after the Big Bang, when the universe underwent a fundamental transformation. High-energy ultraviolet photons from the first stars and galaxies swept through space, ionizing hydrogen gas and making the universe increasingly transparent, potentially affecting the formation of new generations of stars. As we contemplate these ancient ghost galaxies, consider this profound truth. The same fundamental matter that once existed in the primordial universe now forms every atom in your body. We are, in the most literal sense, connected to the cosmic dawn. As we contemplate these ancient ghost galaxies, consider this profound truth: the same fundamental matter that once existed in the primordial universe now forms every atom in your body. We are, in the most literal sense, connected to the cosmic dawn. David Sand's team is developing sophisticated neural networks to automate the search for more ultra-faint dwarf galaxies, potentially uncovering hundreds of additional cosmic time capsules that will deepen our understanding of our universal origins. David Sand's team is developing sophisticated neural networks to automate the search for more ultra-faint dwarf galaxies, potentially uncovering hundreds of additional cosmic time capsules that will deepen our understanding of our universal origins. When you gaze at the night sky, you're witnessing the unfolding story of our universe, a narrative written in starlight that has traveled across unimaginable distances. How does it feel to know you are literally made of the same stardust as these ancient galaxies?